All right, so let's get started. Let's talk about this. What are these things called exceptions? You've actually experienced them already, which is exciting. There's plenty of memes about it because it's just weird stuff you gotta learn. It's kind of the last new piece of C++ that you haven't really learned yet, I would say. One of the last few pieces. So let's talk about it. Exceptions are when exceptional things occur. Okay, so here's like a motivating example of this new concept called exceptions. All right, so let's say that we write a simple function, it's like a division function, let's say. And so it's going to do integer division. Why not? It's called int divide. And it takes two things. The thing that you're dividing, the dividend, right? Dividend. And then the thing that you're doing the dividing by, which is the divisor. Right? Remember those terms? And the simple way to implement that, of course, would be just like return, right? Return dividend divided by the divisor, right? Over divisor, call it a day. All right. But we'll make that one. There might be an issue, right? If you call this in a bad way, you know that if you call it with a divisor of 0, it's going to have a runtime error, right? So how can we fix that? Is there a way to like not make this have a runtime error? Okay. So wouldn't it be nice to not crash the program in this case? All right, so let's code that up to get started. Division.cpp. And I'll call it int divide, int dividend, int divisor, return dividend over divisor. All right, and then of course you can ask the user for the things to divide by. Int n1 equals like 42, and then like give me space for n2. See how we'll divide 42 by something, let's say. Enter a divisor. Cn into that, and then cout divide dividend, 42 n1 by n2. Something like that. And this will work sometimes. Oops. There it goes. So enter divisor 2 is happy, right? Enter divisor 0, oh man, runtime error. We don't like that. So there's got to be a better way, right? I don't want to crash the program when the user gives me a bad divisor to my function. And also, it would be nice, right, to alert the user that they did something wrong. So all that we can do right now with our current knowledge is just add a bunch of if statements, right? Depending on how you want to handle the error, whatever you define that to mean, then like this gets really, really disgusting with a bunch of if statements, right? Like maybe one way that you could do this is like if divisor is 0, do something, right? Cout, yell at the user. This is a philosophical lecture today. And then you still have to return an int though, like you've given up, like you can return -1, let's say, to mean that after you yell at the user. Now you've given up the answer of -1, right? Now maybe it means the answer was -1, now maybe it means no, there was an error. You see that? Like 2 divided by -1, not the, or sorry, 2 divided by -2. The answer should be -1, but now if like we return -1 when there's an issue, we've sort of like confused ourselves. You see that? So that's unfortunate. And so yeah, it ends up involving a bunch of if statements right now to handle the problem with your current knowledge of C++. And that's sad face. We don't like that. All right. So the answer is this new concept called an exception. It's going to make our life much, much easier. It's just a new thing in C++ that tells somebody that something went wrong, that an issue happened. And so we call that an exceptional thing. An exceptional event has occurred. All right. And here's the metaphor. Okay. So exceptions are like, I don't know, a baseball. And they get thrown, all right? Somebody who notices a problem throws an exception, all right? That's the metaphor. An exception gets thrown, and then somebody else somewhere maybe far away in the program needs to catch it, all right? Exceptions get thrown when they happen, and to handle it, you catch that exception, all right? So here's my best drawing of a glove, and you catch it, okay? You catch your exceptions, and that lets you handle them and not have a runtime error, okay? Catch. So that's the idea. Okay, so that's the new thing. I'll show you the syntax right now. Okay, so you've actually already used exceptions, surprisingly, when you mess with a vector and you went to a weird place in that vector. Let me see here. When you went to a weird place in a vector, it threw an exception to you. It was called an out of range exception, and you just didn't catch it, right? We didn't know how to do that, and so when you didn't catch it, it turned it into a runtime error because you forgot about it. But like that was an exception being thrown. Let me show that to you. It's very, very cool. So I'll go to vector. It's a little warm in here today. Let's see here. So you go to .at in a vector. If you go to a weird place, checks if it's within the bounds, throwing an out of range exception if it is not. Ooh, that's kind of nice. All right, so let me show that to you. I think it's like, I guess first of all, let's draw like the example. Let's make a vector 4, 5, 6. So you can go to indices 0, 1, and 2. If you try to go to index 3, for example, though, that doesn't exist, and so it will throw an out of range exception. All right, so let me show that. We try catch.cpp. So let's make a vector of ints, call it v456, and let's go to v at what, right? V at 2 works, but v at 3 will not. Ooh, and so here, terminate call after throwing an instance of out of range. So this is an exception that was thrown, but we didn't catch it. So it turns into a runtime error. All right, but we could have caught it and handled the problem. All right, so the way that you do that is you catch it, use what's called a try-catch statement. All right, so first of all, I want to say every exception that gets thrown is just a value. So this out of range thing is just a class, and somebody made an object of that type. That's what the vector class did, and they returned it. They threw it to you. And you can make an int as an exception. You can throw an int. You can throw a string. That's fine. But people tend to use like purpose-built classes for that. But yeah, it's just a value of some type. That's what an exception is, right? So let's catch the out of range exception and like handle it and not make it a runtime error. Let's deal with it ourselves, all right? So to do that, use what's called a try catch block. And here's the setup. You say try, and then you put braces. It looks a little weird when you first see it, I know. And in between the braces, you put some code that might throw an exception. It's like try to run this code, see as far as you can get into it. So this is code that might throw an exception. Might not. We would like it to run completely. Code that might throw an exception. Okay. And then what you can do is you can catch that exception, right? So you put all the code that might throw an exception, and then you have as many catch blocks as you need for each different kind of exception that might have been thrown within this code, right? So if we want to catch it out of range, you say catch, and then it's kind of like almost a function declaration at this point. You catch, and then you give the type of thing you want to catch, right? So I want to catch an out of range. I'll call the exception E or something, and you generally catch these by reference, and I've run out of room, right? So you should always catch your exceptions by reference. That's just a good rule of thumb to always do that. Out of range, call it E, out of range reference E, and then you handle it, all right? Then you give a body, and then this is where you handle the exception, all right? Handle. The out of range exception. And so if that's the only kind of exception that could have been thrown, you're done. Otherwise, you'll add another catch block with another body for like catch an int, catch a double, catch a bool, whatever kind of thing that could have been thrown. Okay, so that's the idea. So does that make enough sense? This is just code that might throw an exception. You'll never get to here if there is no exception thrown in this code. Sometimes it will, sometimes it won't. Okay. But that's what a try block is for. Try to do this. Try to see if it'll work. Okay? So, yeah, let's wrap this now in a try block. Try to run this line. It might throw an exception. Well, we know it definitely will. And if it does, well, the one that it could throw is an out of range exception. So let's catch that. out of range reference, catch it by reference, call it E, that's the exception object that we've just caught if we get here. And again, what happens is C++ jumps right here if an out of range exception occurs in the try block somewhere, right? And our goal now is to just handle the exception in some way. However we can, all right? So maybe you'll ask the user for a different index to go to, try it all over again. You can handle this in any way. I'm just going to be lazy and I'll say like, uh-oh, and that'll be that, all right? So here's me handling the exception. If I run this now, you'll see that, okay, we tried to do this. There's an exception, an out-of-range exception that got thrown. So we went to the catch block, and then this whole thing is completed, okay? Does that make enough sense? It's a little weird. So let's see here. What do I want to say next? Well, a couple things. First of all, out of ranges, this is an object. Like we caught an object E of the type out of range. So here's the type. The out of range class inherits from all these things. And one thing you can do, it inherits from the exception class. And every exception object has a, let's see. These are all the things you can do to it. There it is. This is how it was declared. There's a method called what that we can call on it, which is very cute. What, and it gives back a C string that tells me what went wrong. Okay, so it's like this is the setup. Okay, we can say what. We can say e.what, and it will give back a string describing the exception. All right, that's a cute name for it. It's like, okay, what went wrong? Tell me. So this is what the exception object has inside of it, and we can say that. We can look at it, and it actually has what's being printed when you forgot to what was it? When you forgot to catch it, like up here. So it's actually it's calling what for us if you forgot to do it, which is nice. And so it's like a text description of what went wrong. Okay, so that's what exceptions get. What else? What else? I also want to say that the try block, it tries to run as much code as it can, but the second one exception happens, it's done. It never comes back. All right, so if I put a good line right here, we'll never get to that line. All right, this line will never get run. All right, I'll just say will never run. Because the second the exception happens, it's like C++ says, all right, something went wrong. Obviously, the rest of this code makes no sense anymore because there was an exception. So I'm going to jump and handle it, and that is the end of the whole try catch. So if you wanted to go to this good line, all right, you'd have to put this whole thing in a loop somehow. Does that make sense? It's all bets are off the second one exception happens, and so it's never coming back to any further lines after an exception. All right, and so even if you have another line that will cause an exception, you'll never get there either. Okay, so it's just the first exception happens, you jump to the corresponding catch block, and then the whole darn try catch is over. Okay, so that is the secret. That's what happens. That's us catching somebody else's exception. So it's vectors.at, notice the problem, through the exception, out into the crowd, and we had the glove right here in our catch block. Okay, that's how it works. All right. Any questions about that before I show you how to throw your own exceptions? So that'll fix the division problem, right? Let's see here. So yeah, you can throw your own exceptions. Usually you'll use one of the pre-made types. You could throw an int though. Standard except is the header that has exceptions. So usually you'll throw a runtime error. This out of range error lives there too. So where is it? Standard except. And so here's all the different classes that you can get. I think I just like to use runtime error in this class. So a runtime error class looks like this. It has a constructor that takes a string, and that will be used to describe what went wrong in the .what. So it's just an object that holds a string, essentially. It's a class that holds a string. That's what a runtime error is. And yeah, there's other kinds, though, that you could look into. Okay, invalid argument exception. You could throw that, and that gives your user some more information about what went wrong. Okay, so that's kind of nice. But yeah, runtime error's constructor takes a string, and it returns that string when you call .what on it. But you could have thrown in it. You could have thrown a double. It doesn't matter. You just throw something of any type, you're good to go. Okay? So let's write a couple throwing functions that notice errors. And this is how you throw stuff. You just say throw. You say throw and then what you want to throw. Like throw 42 and that'll throw an int as an exception. And somebody has to go catch it. You can throw a double. Throw 3.14. And I don't know if I can show it to you well enough in this first lecture on them, but the whole point of an exception is that you catch it far, far away from where it's thrown. All right, that's the goal. It's cool like that. You can talk to people from very far away by throwing these exceptions. Okay, so yeah, let's make a few exception throwing functions, and we'll figure out some cool stuff about it. Okay, throw.cpp. So let's make a few functions that throw things. All right, I'll make a throw string, a throw int, and a throw runtime error function. So I don't know, void throw string. I don't know, let's make a string. I guess I need the string type and the standard except type header. So string s equals blah, and then I'll throw s. So you can throw a string, that's fine. You can throw an int. I'll throw 42. But usually you throw only when you notice a problem. Okay, so like throw 42, and then I'll make one that throws a runtime error. Okay, so I don't know. Let's make a runtime error object. That's all it is. It's just an object of that type. Let's call it RE, and then it takes a string in its constructor describing what went wrong. We'll just say uh-oh, something silly, and then we'll throw that. All right, so it's just another object. You can throw a vector if you want to. All right, you can throw whatever type you'd like, and somebody's job is to catch it. Okay, so let's see here. What do I want to do? Let's make a function that throws one of these, I guess. And we won't know which one, let's say. So let's make a function called do stuff that may throw one of these kinds of exceptions. You got your runtime error, your int, your string, one of those bad boys. So here, let me show them all to you right here. And then let's implement do stuff to like randomly. Let's use cstdlib and ctime. I will randomly pick an exception to throw. All right, so here, let's make a random number between like 0 and 2. Int choice equals rand mod 3. So I'll give me a random number between 0 and 2. And now, if the choice is 0, let's do the throw int function call. Else, if the choice is 1, I'll throw the string, and then otherwise it was 2, so I'll throw the runtime error. Okay, so we don't know. This function is going to throw an exception. We're not sure which kind. Okay, and now let's handle that exception, one of them, all of them, I guess, down in main. So we'll call do stuff, and so right now it's going to throw some random exception, one of these guys, and we are not try catching it. Okay, so let's watch what happens. And do just shout out if any of this stuff's making sense. So let's see which one got thrown. This one threw a runtime error, so it called what for us? It's like, okay, you didn't catch the runtime error. This one threw an int. It's like, okay, you should have dealt with that. And then if you wait long enough, it'll also throw a string. So there it threw the string as well. So like, if we would not like to not have a runtime error, we have to catch these things. Catch the string, catch the int, catch the runtime error. Any of the ones that may have been thrown. Okay, so let's add now a try catch block. All right, so let's see. I'll talk about that later, I guess. Yeah, any questions? So a random number, so some big number, and we're doing mod 3 on it. So when you divide a number by 3, the remainders, right, it can be 0, 1, or 2. That's how it gives me a random number between 0 and 2. Okay? Yeah. So it's very useful for these kinds of things. So let's just say try to do stuff. And then we know that an exception will happen, right? So let's see, and let's catch all the different kinds of things that could have been thrown. All right, so I'll catch. It doesn't have to be in order. It's like whichever one happens, go here. So I need a catch block for example, a runtime error. So I need to be able to catch a runtime error because that might occur. That might be thrown to me. Okay. And so here I am in main. By the way, this is far away from do stuff, right? This is outside of do stuff. I'm catching a problem that do stuff is telling me about. You see that? It's far away. It's different from calling and returning. It's kind of cool like that. It'll just stop. All right. So yeah, catch a runtime error. And what do I want to do with a runtime error? Like the second you put a catch block for something, it's like you're shouting to the world. You're shouting to C++, hey, I know how to handle a runtime error. Choose me. I have my glove ready. All right. I know how to handle a runtime error exception. Okay. I guess I've run out of space here. So I need this. And like, what do we do when we get it? How should we handle it? I guess is now the question. We'll just be lazy about it. We'll just say caught a runtime error in main, and here is like the e.what on the thing, right? Which is the string we put into it. All right. So if a runtime error gets thrown, we can handle it. We go here, right? And then we're good. Also, a string might get thrown. So let's add a catch block for strings. Always catch by reference, string s. And again, this is you shouting to the world, I know how to handle a string exception. Like, come to me. I have my string glove ready to go. Right? Caught a string in main. And then it's just like, we're calling it s. So like, we'll print out the string s or whatever. Like, handle it in some way. And then finally, if there is an int that gets thrown, we can catch that. We should just get into the habit of catching them by references. Right? So I know how to handle an int exception if that gets thrown. Caught an int in main, and here it was. All right, and so now I am set. Right, no matter which kind of thing that gets thrown, I have a catch block for it. All right, in main. And so it was an int, it was a runtime error. Eventually, it will be a string. There. All right, so just randomly it's throwing stuff, and here I am catching them all. Okay, are there any questions about that? Yes. Because that's a runtime error is the class, and there's a method inside of every runtime error object called what. There's no method on strings called .what, and there's no methods at all on it. No, it's just like I know that this is inside of a runtime error. It's like a runtime error is an object, just like a vector, so it has methods on it, and one of them is called what. Yeah. Another question? The one that throws stuff? Yeah. Or like one of these. Okay, yeah, one of these is going to throw them, so like... So did you declare a value called runtime error, or like a variable called runtime error? Yeah, so here I am making a runtime error object, right here with its constructor. It takes a string describing the error, and then I'm throwing that. Yeah. And here I am picking one of those, and so in do stuff, notice it notices the problem, like this line runs in do stuff, and then we immediately jump out of do stuff. This is the power of exceptions. Like the rest of this if else whatever does not get run. If there was code down here, this will never get run, because the second an exception occurs, C++ is like, all right, something went wrong. Where are my handlers? I'm going straight to them. So this is a way to like move around in a weird way in your program, right? It's very, very powerful. I'm not sure if I can like get that across fully today, but like I'm gonna try. Okay, so it goes straight to here. The second something went wrong, and it tries to catch it, because that's where my catch blocks are. All right, and then of course, like once it chooses and it works on one of them, the rest of the whole try catch is over at that point. It's like rest of program down here, That's fine. It's like just the second an exception occurs, it's jumping to the closest catch block. I should say that now, and then it's done with the whole try catch that handled that. All right, and then like rest of program. Okay. Question? Does everything in the do stuff function still occur? No, it's only one. So again, if I had a line right here, never gets run. All right. Even if it was at the beginning? If it's at the beginning, sure. Oh. It's just going to run things in order until it either returns or it throws an exception. So if it was at the beginning, this is fine, but this line will never get run because one of these lines is for sure throwing an exception, and it's going to jump to a handler the second it sees one. Yeah. So say that again? Yes, a try is where you put just normal code that you'd like to run. Just try to do it, though, until an exception occurs. So you might put code that doesn't throw an exception. Like maybe you get lucky and you have code that doesn't run an exception. So it'll run all of the stuff in the try in that case. The whole point is that we're being defensive. We're saying it might throw an exception, so let's get ready. Let's be ready to handle these things. Nice. These are good questions, guys. Good. Let's see. What else do I want to talk about? I want to show you that you can make multiple try blocks. Like it's going to find the closest one. All right. So the first exception gets thrown. By the way, that is when that's when everything stops. So like if I have do stuff twice here, never get into the second one. Never get into it because we're always throwing an exception in the first one, right? Never get into that second one. So it's always immediately caught one int. We go to this int handler, then I'm done with the whole darn try catch. I'm never coming to the second one. The second the first exception happens, C++ is like, all bets are off. Let me handle it and then be done with the whole try catch. So if you want to ever come back, you have to like put the try catch in a loop, maybe remember what you've done so far, something like that. Okay, so yeah, this line will never get run. All right, and then also you might want to separate things. So first of all, I think you kind of get the idea of like if you have a bunch of different lines in your try block and they all might throw different exceptions, like you have a very long try block and like that line might throw a runtime error, that line might throw a double, a bool, whatever. You have to like put a lot of catches, and so you might want to like try to split them up if you can, and you'll need just a ton of catch blocks in that case for every different kind of exception that might occur inside of your try block. Okay, and then let's see here. The last thing that I want to kind of teach you is there's a stack of exception handlers. Essentially, I'll draw a picture. It's a pretty picture, and it will find the closest handler. All right. So before I say these words, let me just show that to you. Okay, so here, I put try catch here in main for all these different things, but I could just as easily, I could put try catches anywhere that an exception might occur. These lines throw exceptions, right? So I could add try catches into do stuff. Okay, that's the idea. I can add try catches into here. Let's see here, and that will actually change how this works. So I'm going to remove that line for later. But yeah, this code right here, right, that they might throw an exception. So let's try to run it, okay? And now you're going to see the power of exceptions and exception handlers, all right? So this code, of course, we know might throw an exception. I can add another try catch, all right? Let's say that if something bad happens and it's a runtime error, like I know how to catch it right here and do stuff. Runtime error. You don't have to go to main. I know how. And so this catch block right here is you exclaiming to the world, again, I know how to handle a runtime error. And I know how to handle it right here up here, closest to the problem. See that? And now it's called a runtime error in do stuff. See that? So I'm closer to the problem. Choose me, pick me, okay? And then you can also catch let's do a string. And so we know how to handle a runtime error in a string up here, but not in it. I know how to handle a string exception called a string. We'll call S again and do stuff. S dot what? I think I have to zoom out a little bit so you can see all what's going on. But here's the idea. Now in do stuff, I've added a try catch. Try to do all these things and then catch one of these if an exception occurs. And now the question is, I've also set up try catches down here for runtime errors, strings, and ints. If a runtime error occurs inside of this function, am I going here, right? Or am I going to go here? What do we think? Yeah, it's going to go to the closest one. The closest one to the issue, it's going to be do stuff. That's closer to where the runtime error occurs. Like this line inside of that function. So like this is a closer runtime error handler. Does that make sense? Another question, yeah. Say that again? Oh no, strings don't have a .what method. They're just strings. Only runtime errors have a .what method implemented for them. Strings have like .size. Usually no, you make your own exception type with all the information that you need. But this is just to show you that you could. So here we go. This is interesting now. All right, so main's like, all right, try to do stuff. I'll set up these handlers if you need me for runtime errors, strings, and ints. And then, all right, do stuff apparently through a string. We got to here. And we also set up a try catch, like, all right, if you get a runtime error or a string, come to me. And this one threw a string and it went right here. It caught the string and do stuff, handled the problem. All right? And then that means this line from main's perspective did not throw an exception. Does that make sense? That's weird. That's kind of cool. And so now this line will work. Okay? Let's see here. So first of all, if I add two do stuffs, remember the very first exception gets handled, and that's the end of the whole try catch. But if an exception gets handled inside of do stuff, it looks like nothing really got thrown to us. And so, like, I can see out here, we will run this line if do stuff handles the problem for us. I'll get here if the error gets caught in do stuff, because then from main's perspective, do stuff returned normally, which is very cool to think about. So now that line will run, now that it caught stuff. So the one that won't do it, right, the one that won't get to this line is if an int gets thrown, and here's that example. All right, so we went to do stuff, set up all these handlers for runtime errors, strings, and ints. Apparently the int got thrown, but we set up handlers for runtime errors and strings, so we didn't handle it and do stuff, so the int kept getting thrown. It's still in the air. And now main, we have to go all the way to main to handle it, and then it catches it. Right? But if it was a runtime error or a string that got thrown, look, apparently a string got thrown, it's now do stuff can handle it. It's like, all right, string got thrown, it'll jump to its closest handler, so now it's good, the whole try catch is over, and do stuff can return normally, as if nothing ever happened. So we caught the error closer to the problem, and then, all right, this line just ran normally. From main's perspective, it's happy, no exceptions. And so, like, we run this line, the error did get caught and do stuff, and then the whole then the whole try is over. We didn't need to go to any of the catch blocks. Rest of program. All right. Does that make enough sense? This is a program to like play around with and mess with things to see how it changes. Yeah.
You said ints and strings and everything else is not normally thrown, right?
Usually, you'd use one of these custom exception classes, or you'd make your own to just like, here's all the data like as member variables that the person who will handle this error needs to handle it. Yeah. Let's see here. Yeah, I think we're getting good now at exceptions, but this is definitely a little complicated, I would say. So let me try and show you why. Like, if the string gets thrown, it's jumping here. It's not going to this one, for example. I want you to imagine that there's a stack of handlers whenever you have a try-catch block. Whenever you're inside of a try-catch block or multiple. Like, technically, when we get to here, like these lines, we're inside of two try-catches, one from main and one from here. Yeah? Two at once. So it's as if we're stacking work just like a function called stack. So, yeah, here we go. So it's building up a chain of exception handlers, little catch blocks, and it knows to go to the closest one if there's an issue. And it's keeping track of which try-catch blocks you are in right now, all right? And that's how it knows like where to go, okay? So here, let me try and draw a picture of what's going on in this program, all right? Let's say that we just started out and like we're on the first line but we haven't run it yet of this try block, all right? So we're in main right now. We're in main and we are in a try-catch now. So we just make our way right inside of these braces. So I'm like, okay, we're inside of a try-catch. And what happens is there's going to be now an exception handler stack. Right now it's empty. Exception handler stack. This is technically what's going on under the hood too. And what happens is like, all right, we're in a try-catch, and it marks, right? It saves for later. Like, I know how to catch a runtime error right now, a string or an int inside of here. It remembers that, right? It's like, it's saying, all right, main, I'm in main. Main knows how to catch a runtime error. Runtime error. Main knows how to catch a string and an int. It's adding all that to its exception handler stack if you need it. Go here. Here's where the bodies are. Int. Okay? So now we're here, and then we call do stuff. All right, so on the stack now, we've called do stuff. Now we're working inside of do stuff. I'll use blue for the normal stack. So now we're inside of do stuff, right? And let's say, randomly, we get to, well, let's say that we choose 2, all right? And then we go to this try-catch block, and we're working on this if, else, okay? So now we're here, and we're again in a new try-catch block, which means we have more exception handlers to remember in our stack, all right? So we know how to catch a runtime error and do stuff, and a string and do stuff. So we're just entering this try block. So it's going to remember. It's going to save, all right, do stuff, knows how to handle a runtime error. Runtime error. Do stuff knows how to handle a string. Cool, it's happy. And that's my stack of exception handlers. And then let's say it was 2, and so we're going to call throw runtime error. And so technically we are going to get to here, right? We're going to call the function throw runtime error. And that's where the issue happens. All right, and that's where the exception gets thrown, right here on this line 19. Okay? And then, all right, the exception handling part of C++ wakes up and it's like, okay, I see a runtime error. A runtime error has been thrown. I'm going to start, it's called popping the stack. I'm going to start throwing stuff off of the stack. I'm going to start looking at it, looking at the top consistently, throwing stuff off until I find somebody who can handle a runtime error, because that is just what got thrown. All right? So like string, nope, you're no good to me. And then it gets to this one, right? It sees a runtime error, like, okay, thank goodness, my saving grace, I'll go right here, right? This is the closest matching handler. That's what I mean by that. Closest matching handler. That's what it's going to go and look for, all right? There is a way to handle a runtime error in main, but that's farther away from the problem. C++ considers like the closer you are to the issue, the more information you have and the better you can handle it. So it's going to go to the closer runtime error catch block. Okay? That's why it goes to do stuff's version of it all. All right? It'll match the first one that works. Okay? And that is my best drawing of what's going on under the hood. Are there any questions about that? That is why it works. All right? And that's why exceptions are beautiful. And yeah, again, the power comes from the fact that we are like, say, like we're in throw int, for example. We are like 2 function calls away from the int handler, but that's fine as far as C++ is concerned. You are moving around you're jumping really far between functions, potentially, with exceptions. Right? And that's where the power lies in them. Okay? So that's what I want to try to get across today. It may not come as obviously as other topics, though. So, yeah, we spent a lot of time on this. Let's fix the division example finally. All right, we're ready for that. Let's throw like a runtime error in the division function, and now we don't have to like do a silly check if it's 0 and like return -1 or something silly like that. Okay, like here's how we would have had to fix it before, right? We would have had to do something like this, like if, before we knew about exceptions, if divisor is 0, then be like cout bad divisor, yell at the user, but then also you have to return something. Return -1 or something like that. And that's disgusting, right? Did it? I hope it compiled. Yeah. Like 2 works, 0, at least it doesn't have a runtime error, but it's like bad divisor, and like, oh, the answer was -1. But what if I gave like -42? Now the answer is still -1. Like, was it bad or was it not bad? Runtime error exception will fix this. All right. So we'll call it division. Spell division, right? Fixed.cp. So I'll include standard except. We're good there. And let's see here. Except. And we are going to fix this divide. All right. Instead of, let's see. We'll throw a runtime error. We'll notice the problem, right? You throw when you notice the problem. You don't have to handle it. The whole point is like somebody else handles it. So we're going to notice the problem right here. If the divisor is 0, we'll just like throw a runtime error. And I'll just call its constructor like this. Error. Just give it the string division by 0. That'll construct a runtime error object and immediately return it. Otherwise, if we're good, like keep going down to here. Okay, and that's the goal there. And now this is beautiful, right? Because now I can see the issue. It's much, much better this way. Division fixed. I don't have to like save away like -1 as some bad answer, which is extra, extra nice. There. So like 0 now. It's going to throw a runtime error, and we just have to catch it, all right? So here's finally a good example of me handling the error properly rather than just printing something, all right? So let's say we would like to, like if we get like some bad value, let's just like keep asking the user until they give us some good value, okay? So like here's what I kind of want to do. First of all, we can do this, right? Let's say something like this. Try, like this, these lines might throw a runtime error, so let's try to run them, and then we'll catch that runtime error if it occurs, right? Runtime error, catch it by reference, E, and then here's what you do, you handle the error, right? Handle the error. And I think what we'll do is we'll ask for a new divisor, right? Just keep on asking until they give us a good one. Asking for a new divisor. And then I have to involve a loop in just a second, so give me a second for that. Can't divide by 0. Try again. So I don't even need to look inside of the runtime error. I know the problem, right? There's only one issue that would have brought me here. This is how you really use an exception to do something. Okay, so again, it's divide that notices the error, and then we're handling it in main, far away from where the issue occurred. Right? So if I type 2, it's happy. If I type 0, it's like, can't divide by 0, try again. At least now it's not a runtime error. And now let's like let them try again. So let's do this. While true, until the end of time, until you give me a good value, user, you're going to keep trying. I'm going to repeat this code, all right? And here's the secret, all right? Here's what I can do. This is kind of cool. If an exception happens, right, we don't even print, right? We just we try to call this function. We don't print anything. We go straight to here and we're done. But if this works, right, if this was a good value, we'd print something and we would move on to the next line, right? So I can add my break right there. See, if an exception does not occur, I'll hit the break and stop the loop. But if one does occur, I'll go straight to the catch block, which finishes off the try catch. We never get to the break, and we'll continue the loop. That's the beauty, all right? So until the user gives me a good value, it's going to keep asking. So enter divisor 0, 0, 0. So it keeps throwing an exception in divide, right? It notices the problem, throws the runtime error. We keep on catching it, and we never get to this line, right? It can be 0 all day long until you want to give me a good value, user. And then I can finally type like -42, and like the answer is, and I know it is, -1. All right, print it out, stop the loop, keep going. All right, so that is a good example of coming full circle and like using exceptions to do something useful. All right, does that make enough sense? So again, we're noticing the problem in divide, throwing the exception, and we're just praying that somebody has their glove up, right? Somebody other than us. Because exceptions, it makes no sense to try to throw and catch in the same function. Does that make sense? No, I've said sense too much now. So it's silly to throw an exception and then immediately have a try catch around that in the same function. You could have used an if statement. There was no point using exceptions. All right. I hope that makes a little bit of sense at least. All right. So throwing a runtime error, the whole point is you notice the error somewhere far away from where you handle the error. That's the idea. Okay, that's what exceptions give you. You could have used an if statement if you want to handle it in the same function. There's no need to use exceptions. But when you're far away from the problem and you want to handle it way over here, that's where I have enough context to deal with it. Then you use exceptions. Okay, that will make more sense the more you read about them and practice with them. But I think that's what I wanted to say there. Any questions about that? Okay. All right. So. Let's see, what else do I want to do? I guess I have a quick exercise for us. All right, I don't know. Do we have enough time for that? Well, we'll see. We'll see. I want you to try it though. I want you to try this. All right, I have given I made a factorial function once upon a time, right? When was that? It's called fact. I made a recursive factorial function once upon a time, right? I guess it was lecture 21, factorial.cpp. Let's look at that. this bad boy, there's actually an issue with this code, this factorial code. If this is my recursive factorial function, right? If I call fact on 0 even, on 0 or -1, any number smaller or equal to 0, do you see that there would be a problem? Like you call fact of -1 or something. Fact of -1, it's like, all right, I'm in the recursive case. I'll multiply my -1 by fact of -2. First of all, fact of -1 doesn't exist. So like, all right, I'll call fact of -2. And then fact of -2 is like, all right, I'll call fact of -3. And then it'll just work until the end of time, right? Just make its way down. So it's an infinite loop, thanks to this line in the recursive case. So don't let the code get here. I'd like you to add an exception, right? I'd like you to throw an exception if you get a bad value given to you, all right? So try to fix this factorial code to handle 0 and -1 and -2 and all those values that are bad, and like throw an exception instead of letting them stack overflow. Does that make sense? So see if you can try that. You can type it wherever you'd like. Write it down on a piece of paper if you'd like. I don't need to see it, but I want you to try it, all right? And let's see, I'll post the code from today as well right now. So if you want to go to the code from class, you can see that too. Let's see. So you should right now have all the code that I wrote today with the try-catch and stuff and the throws. Take this, like even just discuss with your neighbors where you would put the issues. All right, where would you notice the issue? Where would you throw something? Okay? Fix that. What else was I gonna do here? A few more seconds to think about where you'd put it, how you'd write the code, and I'll show you my way. So we'll just do it live. Okay. So let me show you my factorial example here. Let me get rid of that. I'll call it factorial.cpp. I'll paste it in here. And like, what did I have before? Fact of 5. I don't need the iterative version anymore. Let's just be like fact of -1. It's like right now it's allowed and it will cause a runtime error. It will just blow up that stack. All right. So we're going to fix that with exceptions. We'll use a runtime error from standard except. And it's like, I guess let's just try it right now. So I'll call this, let's see here. factorial, factorial. Yeah, so it's going to blow up the stack for a fact of -1. And let's fix that. All right, let's add this exception checking case. So like if, right, the smallest one for my base case is 1. I could have changed that to 0 if I wanted to, but like if n is less than 1, this is not going to work for anybody, for any other number, right? So if that is the case, let's throw a runtime error. Just not continue. Throw a runtime error and just say like can't calculate the factorial of numbers less than 1 sad face. Something like that. Okay? Some sort of string to notice the problem. And now when we compile and run this, it's going to be happy. It's like, we have a runtime error. Here's the information. You should have caught it. That's beautiful. Now I can try catch. So like try to do all this. If we can do it. And otherwise, let's catch. Right? Catch that runtime error by reference and call it E. And I'll see out like e.what or something. That will be my way of handling the problem. All right. All right. There we go. Any questions about like how you notice the error, you throw it up there, and it's somebody else's job to catch it way down the line. Yeah.
So you like throw it?
Yeah. Exactly. Far away, because if I wanted to handle it right here, I didn't need to throw it. Like I could just put in the body the issue, handle the issue. Yeah. But sometimes, usually, you don't know enough to handle it. Like maybe the job is to ask the user for another number to take the factorial of, and that's main's job, right? That wouldn't be factorial's job. Yeah, good question. All right, are we good with that? Because I have one last topic for the day. Actually, it's a new topic for the class, and I might have to just use some pre-written code, so we're kind of running out of time. But I want to teach you what's called functional programming, all right? I promise to not test you on it. It's just a really cool idea. I got really into it in grad school and towards the end of my undergrad. It's just there are some languages that are built in this way. C++ can do this thing called functional programming as well. Just not super easily. It'll look a little weird, but it's just a powerful concept where you think in terms of functions and like what they return and how they work. Okay. So what you've been doing is imperative programming, all right? And there are plenty of memes about this too. So it's fun. It's a little complicated, but it'll be fun to at least talk about, right? So first of all, what is imperative programming? That's what you've been doing, right? It's a way of programming, a paradigm for programming, where you use a bunch of statements and like you write all these lines and your program state changes over time. So like you had a variable, you had a sum variable that held, 0, and now it holds 1. You've changed it. Now it holds 3 because you're summing up these numbers in this vector, for example. Now it holds ... all right, until it gets to the final answer. You're messing with the value of a sum variable. And like at the start of the semester, I'm like, we were using these lines, sum equals sum plus I or whatever. Like these lines, this is not a mathematical equality anymore, right? Because you've changed the value. Normal mathematical variables should not change. And imperative programming is like, we're going to let them change, okay? So you're changing the state of the program through the values of the variables, all right? It's like, that's what imperative programming is all about. You got a sequence of steps, do them in this order. We're going to mess with the values of the variables, and eventually their values will be messed with so much that we have an answer in one of them, okay? So that's not how you know how to think right now. That's imperative programming. That's what you learn in this class, and pretty much most of your computer science classes teach you imperative programming. You're messing with state, all right? Functional programming, or FP for short, is when you disallow lines like this. Every variable is a const from now on. That's what functional programmers are all about. I know the value. It's never going to change, right? You essentially, you're going to write programs by like writing a bunch of functions and composing them, calling them one after another like this. All your variables become constants, and then you're like, all right, I'm going to call this function on this value, and like I'm going to use the result. I'm going to compose the functions, like feed the answer of one into the next one as the input. Okay, that's what functional programming is all about. That's the one change, and apparently people are very, very like they care a lot about this. Okay, there's a fight going on between the imperative programmers and the functional programmers of the internet. Okay, so yeah, that's the goal. And yeah, just like emphasizes like we're going to use constants all over the place. We're going to use functions. We're never going to mutate our data. All right. So every variable is a constant in functional programming. And yeah, let me show you how. What's that? I can't hear you. Sorry. All of their member variables pretend that they would be constants after they get initialized. Sure. Yeah. If you want to mess with them, if you want to do a method on them, you'd have to return a new object. That's exactly right. Yeah, that's a good question. You'd have to, everything is constant. You'd have to return a new object if you want to mess with your current one. Put it somewhere else. It's like you're always making new stuff all over the place. So let me show you how to do this code, right? The sum of vector in a functional programming way. All right, we're gonna use const. We can't use a for loop because like for loops are changing stuff. How do you do this? All right, let's figure this out. Let me show it to you. Let's see here. What do I want to do? I'm worried that I won't have enough time to talk about it, but I'm gonna do my best to type this out. All right, I'll call it sumvec with functional programming.cpp. All right, I might have to copy a different one in, but here's the idea. Okay, I'm gonna make a vector. You better believe it's gonna never change. Constant vector of ints v is 1, 2, 3, 4, 5, and you don't mess with a vector anyway when you're summing it. So that's good. There's my vector, and I would like to sum it up. Right? I like to sum up all the values in a way that is function. Okay? I'll show you. I'll show you how we have to do this. All right? See how like I don't know what's the best way. The sum is sum of the vector v somehow. I got to make a function for this. All right? So I got to go up here and I'll be like, all right, int sum const vector int reference v, and be like, now I have to think really hard. How do I sum up? How do I know the end of this, right? How do I go through all of it without modifying anything? Without using variables that are intermediates? The range-based for loop is a cheating way of doing that. It's still imperative. It's like, what do you do? Like, I can't use a loop, right? Can't use a loop because I'm not allowed to change things, right? Can't use a loop. I need to somehow split up the array, right? I need to get at the first part of the array and maybe the rest of the array, or the vector, sorry. I can't use a loop. What am I supposed to do right here? All right? The answer is going to be recursion. All right? You can sum a vector recursively and never have to mutate anything. All right? So what I'm going to do is I'm going to split up this vector. Right? I'm going to split up the vector into the first thing, the thing at index 0, and the rest of the array. That's a smaller array, right? The rest of the array. And I'll do like something like this. This will be the code. Something like return v at 0 plus the sum on the smaller vector. And to somehow compute that without modifying the original one. And there's a way, right? That's going to eventually turn into the answer. Okay, does that kind of make sense? Because then I'm never messing with anything. I'm never changing the values of variables. I'm just giving new parameters to function calls. They'll be recursive. But actually, you're going to notice that you need another parameter secretly. Sorry. So let me go back to here. So I'm going to do it with normal recursion. Then I'll do it with what's called tail recursion. All right. So you have to think recursively a lot if you want to do functional programming. And there's people have made functions that you will apply that make it easier, though. So here's my vector. And then I also want to pass along an index. Int, where is my current index? Where am I starting this vector? And this will let me do this right. Okay, so I'm going to, again, split up the vector into this, index 0, and the rest of the, rest of the vector. Rest of the vector. There it goes. And here's the idea. I'd like to return v at, right? V at my current index, essentially. Where am I right now? Like index 0, for example, plus the sum of the smaller vector, right? The sum of this vector starting at current index plus 1. All right, it's a little weird to think about, I know, but I think that's as much time as I have to show you. This is going to be the recursive case. That's how you pass the smaller vectors, like tell it to start at this next index, essentially, okay? And this is the first index. At the start, it will be 0, right? I'll call it sum v and 0, all right? then it's like sum the whole thing. But the base case is going to be like cur index is so big it's not part of the vector anymore. So I'll say this. I'll say if cur index, the thing that starts my vector, is like bigger than or equal to v.size, then I'm good. I'm done. There is no real answer, right? I'll return 0 because there's nothing to sum up anymore. Okay, there's nothing left. Invalid index. Sum of all the values of this vector starting from this index that's way past the end of it, like there's nothing there. So like the sum of all those empty things are 0. Okay, and then it will be else for the recursive case. So yeah, I can help you offline understand this, but that's going to be the recursive answer there to sum up a vector. And notice I'm passing brand new things, right? New ints. I'm never changing the value of cur index. I'm passing along a brand new value to a new version of the function. I've never mutated anything. See that? That's a programming paradigm. It's very cool and powerful. I like it. All right. So we got this. That's what's going on, and we can call it, and it will sum the values of these things, and it will do it right. Sum vec fp, sum vec fp. It's very cool. The sum is 15. That is correct. Okay. Does that make sense? Yeah. Question. It is. Yeah. So this is why this is called just normal recursion, and you are exactly right. You're exactly right. What it's going to do is it's going to call it like with the first index. I'll call it sum vector starting at 0, and then it'll recursively like, all right, I need to sum the rest of it. Sum v starting at 1, sum v starting at 2. So for the longer and longer vector, you're using up more and more memory. That's exactly right. And that's a little disgusting. All right. So there's a way to not do that. There's actually, bless you, there's a way to not do it, but keep it recursive. And this is called tail recursion. All right. So let me show that to you. There's a way to not have this problem. That's exactly the problem I wanted to talk about. So thank you for noticing it. So let me show you what's called tail recursion. All right. So tail recursion is when you don't need to make a new stack frame for a new call. So that is when making a new stack frame is unnecessary, even though you're making a recursive call. This is advanced programming. This is really fun to think about. So here, let me take what I had. To make this tail recursive, I need to not have any intermediate work to be done. Like the reason this is recursive and it's going to blow up the stack for larger vectors is I need to do the sum and then add stuff once I get the answer back. I have to wait. That waiting is the problem. All right. There's a way to make it not wait. All right. So I'll call this sum tail. All right. And what I'll do is I'll pass along a third thing. And I'll call that my accumulator. It's the stuff that I've been building up so far. All right. And if I get to the base case, I'm done. I can return what I've built up. There's nothing left. Return what we have built up. And that's what's in the accumulator. All right. All the things that I've accumulated so far. All right. And then now the recursive case becomes a different looking thing. It's like, all right, return whatever the sum of the vector, working your way down to the next index, and accumulating what we had before plus the value at my current index. That's how we're keeping it. We're keeping new values and we're passing it to new calls of the function. It's building its answer up that way. And it's called sumtail now. All right? And notice how there is no extra work to be done. It's like whatever the answer is, it's whatever that gives back. That's my answer. See that? So now we don't have to blow up the stack. All right? So let me show that to you. It's like, all right, we called sum. Originally, what we're going to do is we're going to call sum with v0 and let's see here, v0 and 0 for the accumulator, and then normally you draw it like this. Sum, like whatever the answer is, it's going to be sum v starting at index 1 and then 1, right? But really, like whatever this gives back is the answer, if that makes sense. Like you don't have to blow up the stack. Eventually this will go like sum v2 3 because it's building up the answer right here, and that will eventually hold the answer. And so instead of doing it this way, what we'll do is we'll just replace our current stack frame. That's what C++ will do for us. It'll turn like, all right, you wanted to call it this way? You wanted to return v11? It's like, I'm just going to change that one to do that one instead. Sum v11. There's no extra work to be done. Right? This is very advanced. It's okay if you don't understand it. I'm not going to test you on it, but it's just gonna reuse the old stack frame. That's the idea. Right? We can reuse our current stack frame because there's no extra work to be done after that returns. Just like that's the answer, because there's no need to save any work. All the work is being saved in this accumulator variable, which is, that's the secret, all right? So secretly it's going to do mutation, but we don't think of it that way, okay? So that is a tail recursive sum function, and it will not blow up the stack if you compile with the right flags, at least. And so this is called sum tail, v0, and the accumulator starts at 0, all right? They're both going to correctly produce the sum is 15, all right? Do you see the difference? It's a little weird, right? It's a great exercise to understand what's going on here. Draw it out, all right? That's a tail recursive function. It's saving work. It's reusing stuff. The last thing I want to show you is that like C++ has some functional programming features. There is a numeric library, and there's an accumulate function inside of that would have done all of this for us. It would have done it the good way that doesn't waste any time or memory, right? So it's called numeric. Here it is. And it's called accumulate. Accumulate values within a range. And so what we'll do is we'll call that. This is still functional programming, right? We're using somebody else's function. We're just building up a chain of functions. So the following is pretty much equivalent to sum tail. All right, so it's called accumulate, and I'll include numeric. It is called accumulate. I'll call it like this. It's like it's going to do the loop for me. Or you can think of it that way. From v.begin to v.end, and accumulate starting with 0, of course. It's like that. It's already been made for us. So there it is. A bunch of sums are 15. Okay? And so if you use these functions like this, and just like keep using constants as your answers, that gives you functional programming. Okay? You do have to think recursively a lot more, but there's these functions like this have kind of like made it easy for you, so you can just use those instead. Yeah? You can reason about your programs much easier because there's you know exactly, because everything's a const, you know what its value will be. Yeah. So it's very easy to prove that your program is correct mathematically. That's a big reason why people like functional programming, is because you can immediately see, like, I know this value will never change because it's a const. I know exactly what's going to happen to it. You can reason about it much easier that way. Okay? So, I think what I want to show you next, one last example. Let's see. I'm going to use a pre-made piece of code for this, okay? Because we're running out of time. But I would like to make a program that sums the squares of numbers from 1 to n. You remember that problem from before, right? I'm going to show you how to do that using functional programming, okay? And so there's a lot of weird things, and I'll show that to you. And I have made a piece of commented code for this. So it's, let's see, where can I go to get this? Give me a second. It's going to be in S24. There it is. I'm going to copy into here. S24, 40, numbers, and 23. Some squares, fp.cpp to here. Here's the program. All right. So I've got a square function. We know that, right? That's a function that squares stuff. We'll build that up. And it'll take a number, and it will sum the squares of those numbers. Okay? So like, let's give it 5 or something. Whatever we gave it before. So enter in like 5. And apparently, the answer for the sum of the squares from 1 to 5 is 55. And I've done it 2 different ways. All right? So let me show that to you. The idea of using this in a functional way and composing functions is like, let's have a function to create the range of numbers. That'll create the 1 to n. 1, 2, 3, all the way to n. There's a function called iota. It's a Greek letter that means that will create this range, right? So I'll call the iota function to generate the range, and then I'll give it to a function called transform. There's a function called transform that will take a range and a function to apply to it, and it will transform it. It'll square the 1. 1 squared is 1, 2 squared is 4, 3 squared is 9, all the way to n squared. So it'll generate that new range because it's not mutating anything. All right? That's what transform does. And then accumulate, we know already. It'll sum it all up for us. So all these different functions will work together and give us what we need, all right? Does that make sense? So like use all these together, and that's a functional programming way of doing this, right? So here is a way to generate a vector of numbers. It's called iota, right? It'll generate 1 to n in order, whatever n was, give it that size, all right? And then I will transform all of those numbers like this with a transform call. It takes the range that I want to transform, where I want to put the answer. I'm technically cheating by putting it back into nums, but you could have made a new vector. And then I'm giving it the name of a function. You've never seen this, have you? I'm passing a function's name to another function. That's functional programming for you. Because it's taking that square and it's applying it to all the elements of that vector. That's what it's going to do. Okay? And then finally, we know how to use the accumulate function. There it goes, starting at 0, put them all in. I'm using a bunch of different functions. I should have said const vector, really, but you get the idea. Does that make enough sense? It's a little weird, but it's powerful. You can very easily reason about what's going on because you're watching it work. Okay. And then the last thing that I want to show you, I encourage you to look into this on your own time. There's something called a lambda expression in C++ that lets you make a function that doesn't have a name. All right, because the only reason I needed this square function right here, right? I'm using it once, right? In this call to transform, like to apply that function to every element of the vector. So it's kind of silly to make just a function and like have it be outside if I'm only going to use it once. And so that's where lambda comes in, right? What you can do is you can make a function that has no name that does the equivalent of squaring. It looks like this. This is a square function that has no name. You give 2 brackets, and then you give like what it takes, and then you give immediately code, like return x times x. This is called a lambda, okay? That's a function without a name. You can put it within your code, all right? So let me show that to you. So if you use lambda instead, like we'll generate the range again. We'll use nums2 this time. Generate the range from 1 to n. We'll transform it based on, right, from beginning to end, based on this function. Here I am. I'm passing the square function without calling it square. I'm just like, this is called a lambda expression. Another Greek letter. There's a lot of stories about like where it comes from, which I will not tell you. But here I am passing the square function as an argument, essentially. You see that? It's a function without a name. What it does is it takes something called x and it squares it. I've never called it square though. Isn't that wild? I love that. That's pretty cool. And so it's done the squaring. I never needed to make a separate square function and like pollute the namespace. If I only need it once, I'm good. And then I'll accumulate the values again. Okay, so that's sum squares FP. And that is functional programming for you. Okay, so these will be fun to study, I think. Are there any immediate questions that you have about any of this? Oh yeah, I'll post this right after lecture. So yeah, just like before we go, the last thing I want to say before I let you work is let's talk about the pros and cons, right? People get heated on the internet about this. It's like, okay, what is good about imperative? That's what you're essentially learning in your computer science degree for most of your classes. It's like, that's the way, like, what's good about it? Like, that's the way the CPU is really thinking. It's messing with the values of variables secretly, deep down, inside of its circuitry. And so that's a pro for imperative. Like, that's why you should understand it. Like, that's why we teach it to you first. You also have more control over, like, what's going on and, like, how your memory gets managed because, like, you understand, like, that things are changing, okay? But there's also a flip side to that. There's a reason people sometimes reach for functional programming. Like, all right, it can lead to more complex code, and, like, it's harder to maintain because, like, you have all these states changing, all these variables values changing. You're not sure, like, who changed what and in which way. Especially if you have a bunch of people working on the same code, right? Changing different like member variables and stuff. And so it's harder to like reason about what's going wrong and also to debug it, all right? Because like nothing's a const. Like I'm not sure who messed with this variable, but somebody did it wrong. I have to go and find out who. See that? So that's what imperative is all about. It's good and bad. Functional, there's good and bad to it too. Like People think that functional programming, if you do it in this way, everything's const, just a bunch of functions all over the place. You can watch it work in order, essentially. It's more concise, easier to reason about and prove stuff about. Also, something that you won't really learn for a while is, because all this code is immutable, you're never messing with anything, you're never changing things, you can parallelize it. You've heard of like multi-core processors, right? You can have the program do multiple things at once, and they won't step on each other's toes if you're using functional programming, because you don't have to change anything ever, right? Nothing ever needs to be changed and worried about in that way, right? You use a bunch of pure functions that don't do anything. That's what it's called. A function that doesn't change anything is called a pure function, okay? And yeah, there's cons to that too. It's less intuitive. I know that you didn't really understand this very much. It's something that you have to read about and study for a while until it like clicks, for sure. And there is an issue with memory as well that sometimes the compiler can deal with for you. You do have to you have to think recursively. You have to usually you have to copy a lot of stuff, right? When everything's immutable, you want to change just one piece of it. You have to make a brand new version with that one piece changed, okay? And that's going to waste memory. It's going to waste time for that reason as well. But sometimes you have a good enough language and a good enough compiler, it will deal with that for you, and you'll get the efficiency of imperative while you get the easy to understandness of functional programming. So that's why I liked it, and I wanted to study compilers in grad school. So that's my story. All right. So okay, I think that is everything I want to say about functional programming. I'm not going to test you on that. It's just a cool idea that you might want to look into. All right. And also, you now know exceptions. Okay. Any questions about any of that? All right. So I have talked too long. I was going to give you an extra credit assignment, but I'll just give it to you next time. So it'll be fun though. But that is all that I want to talk about today.